So, hi everyone. It's my pleasure to introduce today's speaker, who is Bart Mennink, and he is currently a professor in Maastricht University and has made significant contribution to the field. And his talk today is about understanding the duplex and its security. So, Bart, the floor is yours.
Okay, thank you for the introduction. Also, thanks for inviting. It took a bit of time before I could give a talk here. So this already 3 years old or so, but it has never been properly recorded. So this was a good chance to do this, and also. And my internet was gone, so now I'm back again. And also this gives a very good introduction to the duplex in general. So it's an overview talk about what the duplex really does on a technical level. So let me first start with the history. And the history starts all with the sponge. In 2007, we had the sponge construction. In the sponge construction, you use a b-bit permutation of C plus R bits. And this b-bit permutation could be 1600 bits, could be something like this, and you split the state into an inner part of R bits and an outer part of C bits. C is typically the capacity, corresponding to twice the security parameter. R is the rate, which corresponds to how fast you can process the data. And if you have to hash a message, a plain text P, it is first padded injectively and then split into R bit blocks, which are processed R bits at a time. So you absorb R bits, you permute, you absorb R bits, you permute, etc. until the last bit of the plain text is absorbed, and then you start squeezing R bits at a time, just as much as you need. It's a very popular design. It's used in SHA-3, for instance. The SOFs in SHA-3 use this idea. Many lightweight hash functions follow this idea, and it was proven that if the permutation is a random permutation, that this construction behaves like a random oracle up to 2 to the C over 2. This is the keyless application. There have also been many keyed applications, and this is maybe a more interesting angle. The idea of the keyed application is that you can just put the key as part of the plain text. Because the sponge behaves like a random oracle, you can do this and it behaves like a random oracle. So you can get a PRF by just concatenating the key and the plain text. This means you can also make a MAC function out of it, stating that if you want to have a MAC function on input of a key and a plain text, and you want a tag size T, you just evaluate the sponge on input of the key and the plain text, concatenate it, and you say we need T bits. You can also look at key stream generation. So you have the key, you have your diversifier, which could be a nonce. You just glue them together and you say we need, well, 5 gigabytes. So you generate a key stream of 5 gigabytes. Those are very popular designs of the keyed sponge. However, these are giving message authentication, they give encryption. They don't necessarily give authenticated encryption. Of course, you can combine it, but you can do it more efficiently. And this is the idea of the duplex. So the duplex main application is authenticated encryption. And there have been many CSAR candidates, NIST lightweight candidates that follow the duplex design. And I would like to take you along with a few historic results in keyed sponges and keyed duplexes. If you go back to the example we saw here, where we just concatenate the key and the plain text, this is what we nowadays call the outer keyed sponge. So you have the key, you have the plain text, you concatenate them, you absorb, and you get your output H. This is what we now call the outer keyed sponge. There have been various works that analyze this result. At some point, there was an interesting observation where you just put the key in the inner part, which is now what we now call the inner keyed sponge. And there was a very nice proof technique inside of this, which I will not talk about in this presentation. But finally, at some point, we realized that if you initialize the state with the key, the state is secret. So we don't really need this security parameter anymore as long as the state is secret. And this led to the full keyed sponge. So this is the previous one where you absorb R bits at a time. In the full keyed sponge, you absorb B bits at a time, which is much more efficient. And the cool thing of this is generically, if the permutation is a random permutation, then all 3 constructions have the same security bound. Of course, you need a stronger permutation, but generically, this all works fine. This was the history of these keyed sponges, but what happened for these duplexes? And the duplex is a bit of a vague construction to understand from the first time you see it. But if you think about the duplex, it's nothing else than a mini sponge, and then evaluated multiple times after each other. So if you look at the picture here, this is the original duplex. If you just stop after the first squeezing, so you have a B-bit permutation, you have an outer part of R bits and inner part of C bits, you absorb P1 with some padding, and then you truncate as much as you need, but you can get R bits, Z1. Suppose we stop there, this is nothing else than the sponge. But instead of just doing a new sponge, we keep the state and we do a mini sponge again. We do a mini sponge again. So a duplex is nothing else than just a mini sponge on an existing state. The unkeyed duplex, not super useful in general. More interesting is the story about the keyed duplex. And here we can do the same thing. We can do this what we now call outer keyed duplex, where you put the key into the first plain text block. If the key is larger, then you just use 2 duplex calls to process the key. So if the key is of size 2 R bits, you would absorb the key. Well, you squeeze or you don't squeeze, it depends. You absorb, you squeeze or you don't squeeze, that depends. But this is the idea of the outer key duplex. Also here at some point, well, we skipped the idea of the inner key duplex. At some point we realize you can do full keyed duplex, because once you initialize the state with the key at the beginning, you have B-bit absorption, so the plain text can be absorbed over the entire B-bit state. Squeezing should be at most R bits every duplex. Because the state needs to be secret. You cannot squeeze for B bits. And this is the main topic of this entire presentation, the full key duplex. Because if you look at this history of the duplex, it is a very powerful construction, but it has never been really estimated at value. So the problem of this construction is that it's often very hard to understand what the power of this construction is, what you can do with it, what's the meaning of this construction. And actually, there have been 3 results that looked at the full keyed sponge, one of me, Reuniterbach, and Vizar, one of Daemen, me, and Van Asch, and one of me and Dobraunig, all looking at different variants of this full keyed sponge, but they were never really fully understood. And this led to, at some point, me writing an article, which is this presentation about, on understanding what this duplex means. And if we go back to this history, so this is the original construction of the full keyed duplex from me, Reuniterbach, and Vizar, 2015. What we see here is we had a bound of roughly this. So this is a simplified bound. So what this means is we have an initialization interface, you have a duplexing interface, you can do initialization, which means you initialize the state. You can do duplexing, where you absorb the plain text, you squeeze, just the way you want it in your implementation. And then we proved that if the attacker has a data complexity M, which corresponds to the number of duplex evaluations, and a time complexity N, which roughly corresponds to the number of permutation calls that it can make, then we had a bound of roughly mu times n over 2 to the k plus m squared over 2 to the c. Here m is the data complexity, so the number of duplexing calls, n is the time complexity, and mu is some multiplicity, which was the maximum outer collision in the permutation. And yeah, this is a long time ago, so this is 11 years ago that we had this result. But looking back at it right now, this is a bit debatable to have this multiplicity there. So first of all, what this means is the scheme behaves like a random duplex, whatever that means, as long as this term is at most 1. I will come back to this later, what this means for such a bound to be secure. But the biggest problem here is that we had this multiplicity term mu, because this is the maximum size of the outer collision in P. And And what is an outer collision? An outer collision in P means the outer are bits. So if you have multiple duplexing calls where the outer R bits is the 0 string, this leads to a high value of mu. But if you think about this, if the attacker can initialize the state, it can make a duplexing call, it learns R bits of the output, then it can make a new initialization, it can make the same duplexing call, but use the outcome of the previous round to wipe the outer part of the state. This increases the multiplicity. So the multiplicity could technically be quite large. There were more problems. Actually, this multiplicity is not a parameter. It's not an adversarial parameter, just like M and N is. Multiplicity is a parameter that depends on the use case, that depends on the power of the adversary. In addition, there was a bound, well, if mu could be up to m, you have m times n over 2 to the k, where intuitively you expect m times n over 2 to the c. And also there was a limited flexibility because the proof is actually blockwise adaptive, where the attacker can make a duplex call, get the result, and make a new duplex call. And then the new duplex call could depend on the output of the previous one. So we did our work in 2017, we generalized this full key duplex, and this became the following construction. And it is a bit of a scary construction if you look at it at the first time. Actually, every time I look at it, it is a bit of a scary construction. But I will still go over it because this is leading towards the main duplex the way we know it today. What we did here is we had previously the initialization was just putting the state, and then the duplex was absorb, permute, squeeze. Now the initialization actually takes the initialization of the state, permute, squeeze, absorb. And then every new duplex corresponds with permute, squeeze, absorb. What happens in some duplex? So you permute, you squeeze R bits, and you absorb B bits. The B bits is the B bit plaintext. It is an outer part and an inner part, left part and a right part. Squeezing is only R bits. So every duplex call gives you these R bits. What else happens? There is some flagging. And the flagging could be, it's a Boolean, it's either false or true. If it's false, you keep the state. If it's true, you override state. So that's the main difference. So first of all, we now initialize the state with a key and some IV. The IV could be a nonce, it could also be a constant, it could be something like this. This depends on the use case of the duplex. We do full state absorption, we don't do the padding. So in the previous picture, we always did a padding, which was a bit of a clumsy approach. So you always had to have an injective padding, so you're wasting one bit. We don't do this anymore. We rephased, so instead of absorb, permute, squeeze, we now have permute, squeeze, absorb. And we refined the adversarial strength. So instead of using the online and offline complexity, we had extra parameters which correspond to many different things. In detail, we proved the following result. We say if the attacker has a data complexity M, a time complexity N, Q initialization call, so you re-initialize Q times. Q IV initialization calls for a single IV. This is typically the number of users in the multi-user setting, number of different keys that you can attack. The number of queries with a repeated path, which means that the attacker can initialize, it can make a same duplexing call. Well, it can initialize, it can make a duplexing call, it can make another duplexing call. Then it can re-initialize, it can make the same duplexing call, but then a different one. Then you have two different duplexing calls with the same preceding path. This influences security, so this is the value L. We also had some weird parameter omega, which corresponds to queries with overriding outer parts, where the flag is true. I will come back to this later too. And some multi-collision coefficient, which is typically a small number. So it's already getting a bit more scary. So the scheme gets more scary, the parameters get more scary, the bound is still simple because this is a simplified bound. But things are getting more scary. What happened in 2019? Well, we thought like, well, let's rephase again. So instead of absorb, permute, squeeze, instead of permute, squeeze, absorb, the duplexing call is now squeeze, absorb, permute. And the initialization is different. So the permutation is at the end of the duplexing call. What other features do we have? The initialization could be rotated. It's not in the picture. We did this rephasing. Why did we do the rephasing? Because we wanted to prove leakage resilience. And to bound this properly, we typically had to take into account the next permutation call already to properly upper bound the amount of information that the attacker could get in the leaky setting. But the bound was similar. So I will not talk about leakage resilience in this setting, but the red parameters Q delta and R correspond to leakage in this case. And the lambda in the bound is also leakage. But this was the state of the affairs. So we all of a sudden got a much more complex bound, a much more complex looking scheme. It is actually a super powerful scheme. It implies a lot. So many permutation-based schemes follow from the duplex. But this was never really properly acknowledged. And this is in part because the scheme is complex. And also this flag is scary. What does this flag mean? The bounds, they got super strong, but the security parameters are hard to understand, and the bounds are quickly misunderstood. There was an application of the Zodiac authenticated encryption scheme, which was based on the bounds of the duplex, and they misinterpreted our bounds. It's actually also unclear what use cases follow from the duplex and how the bound corresponds to these use cases. And this article, this presentation, gives a whole explanation of the duplex, the history of the duplex, its security, and some applications. And I will capture most of those also in this presentation. And let me start with understanding the duplex. So this is now the newest duplex as we know it today. So what this means is that suppose you need to design a key stream generation or an authenticated encryption scheme or just a permutation-based encryption scheme. Many of those schemes you decide to design, you can design on top of the duplex. So this means that a friend of mine made a good permutation. This permutation we can use as a black box to make this duplex. This duplex has two interfaces, an initialization interface and a duplexing interface. And you can use these two interfaces as a black box to make your encryption scheme, to make your MAC function, to make your authenticated encryption scheme, to make your key derivation function, to make your PRNG. That sort of things can be built on top of this duplex. And in these duplexing calls, you call the initialization interface when needed, you call the duplexing interface when needed. And this duplexing interface either gets plain text of B bits or not. You ignore the squeezing or not. The flag depends on the use case. And this is the duplex that we know today. So you have an initialization which just initializes the state, nothing more. You have a duplex that consists of permute, squeeze, absorb, nothing more. And that's it. And the scheme that we know today is now basically the scheme of Daemen et al. 2017 and Dobraunig and me 2019. But then also, actually, the initial state could be rotated. It's not depicted here because that made it a bit of a more complex picture, and it is already quite complex. And we took a different phasing than the previous ones. The cool thing is that the results that we saw before carry over. But let me first go over the understanding of the phasing of the duplex and what this flag means. First, a bit more on the phasing. So if you think about the duplex in a general setting, we always first absorb, either like initialization is also just absorbing. So it's setting the state to a certain value. So you absorb, permute, squeeze, absorb, permute, squeeze, absorb, permute, squeeze, as long as you want. That's the idea of a duplex. In 2011, this construction had absorb, permute, squeeze as initialization. Well, actually, it didn't initialize. Absorb, permute, squeeze, duplex is also absorb, permute, squeeze, absorb, permute, squeeze. The idea of this is that the original proof reduced the security of the duplex to the indifferentiability of the sponge. And this way, the duplex is just a mini sponge. But this also gave the attacker a lot of power because this was a blockwise adaptive proof. So the attacker can do absorb, permute, squeeze. It gets the output, and the next absorb could depend on the previous squeeze. So this gave the attacker a lot of power, which it doesn't always have in applications. And this also gave it a more complex proof. In 2015, when we did the full key duplex, we took the same approach. We got a tighter bound, but also this blockwise adaptivity, so it was not a very good bound. That's why we had a specific proof in 2017. It got an improved bound, but you do the restructuring. So you permute, squeeze, absorb as a duplex. This prevents this blockwise adaptive power that the attacker has. But you needed this flag, and this flag I will show in the next slides. We shifted the duplex. We included the upcoming permutation call because we wanted to prove leakage resilience. And for leakage resilience, we assumed that the attacker learns information from the next permutation call. Now, this seems to be the most useful phasing. So it's the one from 2017, but with the initialization just separated. Now, what about the flag? The flag can have two parameters. It's a Boolean. Can have two values. It's either false or true. So if you have a false flag, then in the top picture, so Z is the output, R bits. False means that you take this value and you add the plain text over the entire state. So this is equivalent to a duplexing call that you see in the top right of the slide. If the flag is true, then you just say 0, which means nothing else than just wiping the outer part of the state. And where is this useful? This is useful for authenticated encryption. And to show you this is a good example of this is the extreme simplification of sponge wrap. Later on in the presentation, I will talk about the actual sponge wrap the way we know it today. But this slide is about the extreme simplification of sponge wrap. This can also be seen as the simplest authenticated encryption scheme that you can do with the sponge. What do? We take the simplest authenticated encryption. We have a key of R bits, we have a plain text of R bits, we have a ciphertext of R bits, and we have a tag of R bits. And we have a nonce U of C bits. Why do I take nonce U? The U stands for unique. I could have taken nonce N, but N is already the time complexity. So I take nonce U for unique. C bits, everything is R bits for the rest, nonce U is C bits. And then this is my authenticated encryption scheme. So we have an initialization of the state with the key and the nonce U. You just glue them together, you get a B-bit state. You permute, this is my duplexing call, where you squeeze R bits. This gives you a key stream which is added to the plain text to get the ciphertext. The plain text is also added into the outer part. And then you do another duplexing call. And in this duplexing call, you don't absorb anything, you just squeeze R bits, and that's the tag. And this is the simplest way of doing authenticated encryption with permutation. So we have a key of R bits, ciphertext of nonce of C bits. You do one duplexing call where you permute, squeeze, absorb. The squeezing is the key stream, which is added to the plain text to get the ciphertext. And then you do a duplexing call where you squeeze to get the tag. This is encryption. And if you think about how decryption looks, we have to revert this key stream generation plain text absorption thingy, which gives you this decryption. And here you see this purpose of the flag. If you go back to what this flag means, if you take flag is false, you absorb data. If you take the flag is true, you override data. And by supporting this flag, you could hypothetically take my friend's permutation. In my duplexing interface, you can implement authenticated encryption just with this initialization interface and this duplexing interface. So I can give you an initialization interface, I can give you a duplexing interface where you absorb R, where you can absorb B bits, you can squeeze R bits, you have this flag. You make an initialization call, so you make a duplexing call with a flag false, you make another duplexing call with a flag false, and you have your encryption. And for decryption, you make your duplexing call with flag true, you make your duplexing call with flag false, and you have your decryption. So we have a duplexing call with flag as true upon decryption, and the attacker typically can choose the ciphertext. And this needs to be supported. Now, what about the security? And what do we need for security? If you think about this, this is quite hard to capture, but we would like typically in the crypto world, we always want stuff to look random. And this is the interface I talked about. So if we don't look at the picture anymore, we look at an interface. This is the setting. So a friend of mine made a very good permutation. We assume that this is a perfect permutation because this friend of mine is a very good designer. So this permutation is perfect. And then I'm using this permutation to build a duplexing interface. So we have the initialization interface and a duplexing interface. In the initialization interface, what you can do is you can give me some key parameter delta, which is between one of the and the mu keys, because we look at multi-user or multi-key security, and some IV coming from some IV space. This may be a non-space, this may be the entire B minus K bit space. It could be anything. It doesn't matter yet. It's just the IV space. What does the initialization do? It initializes the state with some rotation by alpha, it doesn't matter that much, of the key concatenated with the IV. And that's it. That's what the initialization does. It initializes the state. Then you can make a duplexing call on input of a flag, which is true or false, and some B bit plaintext. And what you get is you get your R bit output. What does the duplexing call do? Duplex consists of permute, squeeze, absorb, and that's what you see in the algorithm. So you permute, you squeeze R bits, and you absorb B bits, possibly with flagging. So this flagging kind of makes sure that you overwrite or not. And what you output is your R bit state. And what we would like is that this looks random. So the squeezing should always look random, except if you do the same thing. The same for a random oracle, actually. So if you do the random oracle, you evaluate it twice on the same plaintext, you get the same output. Here, you should intuitively have the same. So if you initialize and you get a duplex, you get some random value Z. If you initialize the same with a different IV and delta, then you will get a different independent Z ideally. But if you initialize with the same delta, the same IV, and then you do a duplexing call with the same plaintext, you should get the same Z. So you should ideally, or ideal duplex gives you a random Z up to repetition. And the way we implement this is with, an ideal duplex. The original naming is a bit of an unfortunate naming. I prefer ideal duplex more, but the formal naming is the ideal extendable input function. And the ideal extendable input function is not based on a permutation, but a random oracle RO. And instead of keeping a state, it maintains a path. And the path is a summary of everything that happens up to the duplex point. So if you initialize the path with the encoding of the key index and this IV. And then in the duplexing call, it has the same interface, flag and a B bit input, and it gives you an R bit output. The R bit output is a random oracle on input of the path and R bits. So you say we need R bits. Okay, so it takes the path up to that duplexing call. It uses this path to output R bits. And then it updates the path by everything that's happening during that duplexing round. So envision the system that you have an IV, then you make a duplexing call, you make a duplexing call, and then you make another duplexing call. Then you reinitialize, same initialization input, same duplexing call, different duplexing call, then the path up to that duplexing call is always the same. So the key stream will be the same. But once you have a different duplexing call, the path will be the same and everything else will be random. So if you think about this, the ASICRYPT is basically a random oracle in disguise. And we say that a key duplex is secure if basically this distinguishing advantage that we always distance from the key duplex to the ASICRYPT is small. So if for any distinguisher, it's hard to distinguish the key duplex on the left of the slide from this ASICRYPT on the right of the slide. So we say basically that the key duplex is hard to distinguish from the ASICRYPT for a certain bound on the adversarial resources, then it behaves like a random oracle. And this bound on the adversarial resources actually depends on this use case, because what I did, I had my friend's permutation, view my initialization and duplexing interface, and you're using this for a certain purpose. Think of key stream generation, think of authenticated encryption, and depending on this application, these adversarial resources differ. And this is proven. So the original proofs of Daemen et al. And Dobraunig and me in 2019, they apply. So we had this online complexity M, this offline complexity N, we had the number of initialization calls, we have the number of calls for a single IV, which is typically the number of keys that the attacker can attack, the number of queries with a repeated path, the number of overwriting queries, and some coefficient, which is typically small. And we had this simplified security bound. This means that the duplex is small. The duplex behaves like a random oracle as long as the parameters are in such a way that this bound is less than 1. And that's the result. Those are the two main results. And it looks cool. It looks powerful. But you may wonder why it didn't really get used a lot. And the reason is that the bound is not actually this. This is an extremely simplified bound. The real bounds are these. And they scare a bit because you see this N, you see the M, you see the Q, you see the L, you see the omega. There is still the multi-collision coefficient, so it's a complex bound. Even the one from 2019, I already simplified a bit more. But the cool thing is that depending on the use case, many of these terms disappear. And to show you this, I will discuss 5 use cases, starting simple and then go a bit harder, to see what's the meaning of these bounds. And the first one is truncated permutation. That's the simplest use case of the duplex. What's the story behind truncated permutation? If you know a bit about this PRP, PRF conversion story, there has been tons of research publications on the security of turning a PRP, like a block cipher, into a PRF. Think of the sum of permutations, think of EDM, EDMD, summation truncation hybrid, truncation. And at some point, this led to forking into a different angle of research of random permutation to PRF conversion. Think of the sum of externally keyed permutations, so sum of Evan-Mansour keyed sum of permutations, permutation-based EDM, but also truncation. You can do truncation from a public random permutation to a PRF. And they can be described with the duplex, and this is what you see on the top of the slide. So let's look at the algorithm first. So we have a key of k bits. We use a b-bit permutation, so we have a key of k bits. We have an input x of b minus k bits, and you get an output y of r bits. And then we just define truncated permutation on top of the duplex. So we take our duplexing interface as black box, and the initialization, well, in the algorithm, it gets its input 1, x, because in my applications, I just take a single key setting. So 1 means the first key, but there's only 1 key, so you can forget about that. X is the input. This means if you look at the picture, you initialize the state with the key and x, concatenated, and then you make a duplexing call. The duplexing call takes flag false. It doesn't absorb anything, so it absorbs the b-bit string, and you get r bits, and that's it. So this r bits will just be my return of the truncated permutation. So the truncated permutation is described in terms of the duplex. And the security follows. Because if you think about what security would we need of this truncated permutation, we want it to behave like a random function. So typically we want to have security of the truncated permutation. We want to look at what we call PRF security, which is the distance between the truncated permutation on top of the permutation and the key. The distance from this truncated permutation to a random function, which I now call RPRF, which is a random function with the same domain and range as the truncated permutation. This is typical statistical. This is the typical distinguishing advantage that we see in these proofs. So we have a distinguisher T who can make Q queries to the truncated permutation of the previous side. It can make N primitive calls to the permutation, either forward or inverse. And it has to distinguish this truncated permutation from random. So how can we prove this? Well, we do the observation that the truncated permutation with based on this permutation P, the one from here, is nothing else than a truncated, well, it's not a truncated permutation on top of permutation, it's a truncated permutation on top of the key duplex on top of a permutation. That's just an equivalent description that we saw on the previous slide. So now by a simple triangle inequality, the PRF security of the truncated permutation from random is nothing else than the second equation. And then we do a triangle inequality, namely we take the truncated permutation on top of the key duplex, the distance from this one to the truncated permutation on top of this ASIACRYPT, this ideal duplex, and then the distance from this ideal duplex to random. But the cool thing of this ideal duplex, this is a random oracle in disguise. Every time you take a different input, you get a random output. So the distance here is 0. I mean, this random oracle in disguise is just a random oracle. So if you look at the algorithms, you get random output every time. Then for this one reduces to the key duplex security. It reduces to the security of the key duplex for some distinguisher D prime, where D is the PRF distinguisher making Q queries and N primitive queries, is the second bullet on the slide. D prime is the distinguisher on the duplex with all these complex parameters. So we somehow have to turn the complexity of D into the complexity of D prime. So let's see, what are the resources of D prime? We have M, we have N, we have Q, we have QIV, we have L, and we have omega. These all resulted in these huge bounds. But for D, the main distinguisher, the PRF distinguisher, we only have Q and N. What about D prime? Well, N is the same. N is the number of permutation calls. Now, Q and M, capital Q and capital M, those are the number of initialization calls and number of data complexity, number of construction calls. That's just the same as a small q of D. Because every time that the distinguisher makes a new truncated permutation call, this induces one initialization and one duplexing call. QIV is 1 because we look at the single user setting. So every value, well, the IV in this picture is X. Every X occurs once. Also, every X is new, so you never have a repeated path. And if you look at overwriting path, the flag is always false. So if you take these values, M, N, Q, QIV, L, and omega, you put it into the big bounds, you get a much smaller bound, a much more concise bound. And this is the security, PRF security of truncated permutation. Note that we have this multi-collision coefficient nu, that's just a small number. Think of 5, think of 7, something like this. So this is n over 2 to the c. This is roughly n over 2 to the k. This is birthday bound in B. This is actually not a tight term, but this also, I mean, a dedicated proof would have given a better bound. But this is a good example of how the duplex can be used for something bigger. And what else can we do now? Parallel keystream generation. This is not spectacular. So what we do is we just put the previous one in counter mode. So I call it parallel keystream generation. We have a key, we have a nonce u, a unique value u. It gives you a key stream of the requested length. This is not an interesting use case. It's just the truncated permutation put into counter mode. So we have a nonce, which is u, which is just slightly smaller than b minus k bits. So it's b minus k minus a bits, where a is just the counter. And you just as input of you initialize with the key, the nonce, and a counter, and you key stream. And the security easily follows, because from the previous use case, truncated permutation behaves like a random function. Counter mode with a random function is random. And more interesting is sequential keystream generation. And in sequential keystream generation, we have the same idea. We have a key, we have a nonce u, and then you keystream r bits at a time. So this is the example that you saw on slide 2 already. In slide 2, I already mentioned this. You have a key, you have a nonce, you initialize the state with key and a nonce. If you need to encrypt a 5 gigabyte data, you squeeze until you have a key stream of 5 gigabyte bit, which is added to the plaintext to get the ciphertext. You can do this with the duplex. So this is a specific case of the keyed sponge, but you can also describe it with the duplex as you see in this picture. So we initialize the state with 1, u. If you look at the algorithm, key duplex dot init 1, u. 1 means we take the first key because we look at a single user setting. U means the nonce u, which is always unique. Important, nonce is always unique, so the path is always different. The path towards every duplex is unique every time. Every duplexing call is just a duplex call with flag false. We never overwrite a state. And the security analysis is comparable, but the resources slightly differ. And to see this, we also want to have PRF security of this one. So we have the PRF security of the sequential stream cipher. It's just the distance, the distinguishing advantage, the distance between the sequential stream cipher based on a permutation from a random function RPRF with the same domain and range as the sequential stream cipher. The distinguisher can make Q queries in total of sigma blocks, which sigma means actually the number of duplexing calls, and n primitive queries. We have the same story, the triangle inequality, reduction of the distinguisher D, of the PRF distinguisher D, to the key duplex distinguisher D prime. And then we have to do the same exercise again. What are the resources of D prime? Same picture, capital M, capital N, Q, QIV, L omega. N is N, Q is Q, capital M is sigma in this context, because sigma is the total complexity of the encryption, the total number of blocks, which is the total number of duplexing calls. QIV is still 1, L is 0, because the nonce is always unique, so you never have a repeating path. This gives you a slightly more complex bound, not that much more complex, but roughly you get sigma times Q over 2 to the B and sigma times Q over something. This is not a main difference. You get a very good bound for keystream generation. And this is an interesting application, message authentication. And there we see this role of this repeated path. So we see what this value L means. And let's go back to the original full-keyed sponge. So back in the old days, we had this full-keyed sponge before the duplex really got famous. We had the full-keyed sponge. And in the full-keyed sponge, well, the picture here is a full-keyed sponge in terms of the duplex. We initialize the state with the key in the IV. We make a permutation call, we absorb B bits at a time, permutation call, absorb B bits at a time, permutation call, absorb B bits at a time, where the plaintext got injectively padded with a 1-0 padding. And then we squeeze permute, we squeeze R bits. You cannot squeeze B bits because the state needs to be secret to the attacker. but you can squeeze R bits just as much as you need. So if R is 256 and you need a 512-bit tag for some stupid reason, then you just have to make 2 calls to get a 512-bit tag. And the picture you see here in the algorithm on the right, this is the full keyed sponge or the full state keyed sponge described on top of the duplex. So we have the permutation, we have the initialization and the duplexing interface of the duplex. And using these two interfaces, we describe the full state keyed sponge. Full state keyed sponge gets some IV, which could be anything, or it could just be the 0 string, a plain text of arbitrary size. The first step of the algorithm just pads injectively 1,0 padding the plain text. The tag is 0. We initialize the state with, well, we take the first key and some IV. Then we make a duplexing call. With flag is false, the first plain text block, we discard the output. That's the comment in the algorithm. We don't care about the squeezing here. We ignore it. So you have black box access to the key duplex. You make a call with flag false, plain text PI for I is 1 to W. And then you squeeze, you absorb, you ignore the squeezing. The picture slightly mismatches because the injective padding is included in the picture. And then you start squeezing just as much as you need. We need T bits, so you squeeze just as much as you need, always with flag false and with plain text 0 because we don't absorb. The old analysis from 2015 did approve of this, but this one had this multiplicity term. This was not a tight proof. But now security carries over. So we have a comparable analysis to before, but the attacker can repeat a path. So what the attacker can do is can make a key sponge calls where P1 is the same for 2 queries, but P1, P2 is different. So you make 2 key sponge evaluations with the same P1, but a different P2. This means that the path towards this duplexing call is the same, but only then you start to incur a difference. So the attacker can repeat the path, and this influences the resources of D prime. In more detail, same story, PRF security, we want a full keyed sponge to behave like a random function. The distinguisher can make Q queries with sigma blocks and N primitive queries. And we again have the triangle inequality, which means that the PRF security of the full keyed sponge against this distinguisher D is upper bounded by the key duplex security against the distinguisher D prime. And again, we have to map the complexities of D to the complexities of D prime. What do we have? Again, Q is Q, N is N, M is sigma, QIV is 1 because we look at the single user setting. But now the attacker can repeat a path. Well, we always have flags false, so you never have an overwriting out part, but the attacker can repeat the path. Every time once the attacker makes a full key sponge query, the next full keyed sponge query, which are Q minus 1 in total, may repeat a path of the previous one. So in terms of the picture, the attacker can make a full keyed sponge query for some IV, which it can always keep the same, P1, then P2. The next keyed sponge query can be for the same P1, a different P2. The third key sponge query can be for the same P1, a different P2. Fourth query, same P1, different P2. So all follow-up keyed sponge queries can be done for the same path prefix. So this means that L may be up to Q minus 1. And if you plug that one into the big massive bound of this key duplex, it's getting more and more complex. So the truncated permutation was simple, sequential key sponge a bit more complex. Now even more complex. What's added? This is the term that gets added. And the main important one is actually the first part of this green term, which is Q minus 1 times N over 2 to the C. Or simply said, Q times N over 2 to the C, which is the influence of L, which is the power that the attacker has in repeating a path. And this term is tight. So to see this, remember Q times N over 2 to the C. So that's the dominating term here. Q is the number of Keats-Ponch calls, roughly. N is the number of permutation calls that the attacker can make Q times N over 2 to the C. Where does this occur? To see this, let's look at the simplified setting. So consider the simplified Keats-Ponch, no IV, no padding, just an R-bit tag. Then you can imagine an attacker that makes two queries. So one query that has a P of B bits, and it gets a tag, which is the picture on the left. So I said no IV, so you have a 0 IV, state initialized with key and IV. Then you do a B-bit absorption, you get an R-bit tag, so that's the first evaluation. And then it makes a second evaluation with the same IV, because we have no IV, same plaintext, but the plaintext is longer, so we also have the tag and 0. So the previous tag is taken and it's absorbed. And then you get a new tag. If you look at these two evaluations of the full Keats-Ponch, we know that the state before squeezing is 0, starts with R zeros. Technically, if you look at the path up to the second duplex, it is identical in both. So the path up to the second duplex in the first picture, so the second dashed line in the first picture, the path up to here is just the plaintext. If you go to the second picture, the path up to here, the path up to the second duplex is just the plaintext. And only then you start doing something different. So here we only squeeze, here on the right picture we absorb. So you have the same path going to a different duplex. And this led to two duplexing calls where we know that the outer part is 0 Rs. What the attacker can do, it can make these Q twin queries for different plaintexts. It can make n primitive queries of the form 0 R and something to the C, and at some point it's a bingo. At some point with roughly Q times n over 2 to the C, there is a collision. And once you get a collision, you can get the key. How can we solve this? A good way to solve this is in the ASCON PRF. So ASCON PRF does a full Keats-Ponch. Well, it doesn't do a full Keats-Ponch, it just does a Keats-Ponch with an R-bit absorption. But it does domain separation right before squeezing. So it just flips a bit in the inner part right before squeezing, and by doing so, well, repeated paths may still occur, but the attacker cannot exploit them. And what happens here is that a repeated path will always end up to an absorbing duplex. You cannot have a repeated path where one of them ends up in an absorbing duplex, but the other one in a squeezing duplex. So actually we thought like, well, this attack doesn't work, you should get a better bound. It turns out that it was not as simple as that, because the parameters stay the same. If you go to the proof of 2017, there was a loose bounding for there. So this term still appeared there, but if we solve this loose bounding, the magic term vanished. In 2019, there was an extra parameter that solved this, so we get a better bound. And also for ASCON PRF, so we get a better bound, this term vanishes. So if you go back to the full Keats-Ponch bound, which is this guy, the green indicated term vanishes for ASCON PRF. And then you get a pretty good bound for ASCON PRF. So we did the analysis. So this is the ASCON PRF bound for the multi-user setting. So in the multi-user setting, the last two terms are a bit different. So you get mu times n over 2 to the k. We looked at what this means for the actual parameters. So if you take the ASCON parameters, you get a key of 128 bits, you get a state of 320 bits, you get a C of 192, a rate of 128. Note that C plus R equals B. If we assume an online complexity of Q and sigma up to 2 to the 64, then the multi-collision term, this nu, is roughly at most 5. I just did the computation. And you get a bound of this form. So 10 times n plus 1 over 2 to the 192, some negligible term, negligible term, negligible term, mu times n over 2 to the 128, and a negligible term. This is actually the dominant term. So you get generic security as long as the offline complexity is at least as opposed to the 128 over mu. And now the main application of the duplex. This is the, I think I only got 1 hour, but I will just finish my slides. I will just be rude. I hope you will not kick me out if it's 11. The fifth application is authenticated encryption. And in authenticated encryption, what we have is we have a key, we have a nonce, we have associated data, plain text, and the output is a ciphertext and a tag. And the ciphertext encrypts the plain text, and the tag authenticates the nonce associated data and plain text. Compared to this is the authenticated decryption. And I assume you know most of authenticated encryption, what's the security model, that kind of stuff. The cool thing of this duplex is that it allows to process different things in a different way. So you can absorb associated data, you can permute, you can absorb, you can use a duplexing call for absorption, you can do a duplexing call for encryption, you can do a duplexing call for tagging. And the flag makes it decryptable. And if you think about permutation-based authenticated encryption, there is this seminar sponge wrap construction from 2011. When the duplex was introduced, they also introduced the sponge wrap. But looking ahead, it's not the most beautiful design retrospectively. It's an important design, but looking back at all we know about the duplex now, there are some weird things. So first of all, you have the one padding everywhere. So every duplex call makes a one padding. Where does this come from? This comes from the original proof to reduce it to the sponge indifferentiability. But in practice, we don't need this. Then there is a domain separation, which is the red bit everywhere now, which is a bit off phase. It actually indicates what the next permutation call does. You really see this if you look at the 0 corresponding to the AV minus 1, so the penultimate associated data block, it gets a 0, but the last one gets a 1, which means that the next duplexing call corresponds to encryption. We don't use the inner part, but you can use full state absorption. Also, there is no explicit nonce. The nonce is hidden in the associated data, which is fine. I mean, what's the difference between the nonce and associated data? And the key is blockwise, but nowadays we know you can do full state absorption. You can just initialize the state with the key. And if you take this all together, what we get is in 23, I described this monkey sponge wrap. A monkey sponge wrap is nothing else than the monkey duplex with sponge wrap as the duplex. And well, it's a cleaned up stuff. So what happens is we initialize the state with the key and nonce. Initialization is key and nonce. Then we do duplexing calls to absorb the associated data R bits at a time. So every duplexing call absorbs associated data into the state. Then we do encryption calls to, then we do duplexing calls to encrypt R bits at a time. So the plain text is split into R bits. We encrypt by generating a key stream, adding it to the plain text, you get ciphertext, and you absorb. Why do we need to absorb? So far, if you look at the dashed line after the absorption of P1, the state there, yeah, well, you can see there's a key summary of all the associated, of the nonce of all the associated data of the plain text. Then another duplexing call for encrypting P2, another duplexing call of encrypting P3 up to PW-1, where the plain text is cut into R-bit blocks. Another duplexing call for the last plain text bits PW. This means that the state up to that point is a keyed summary of nonce, associated data, and the plain text. And then we start squeezing the tag. So the tag is the tag on input of all that's absorbed. We do a domain separation, which is in the inner part. For associated data, we don't do anything. We just flip a bit whenever we do encryption. And that's the monkey sponge wrap. And it's a very popular design. It's used in many authenticated encryption schemes. What about decryption? In decryption, it all remains the same except for where encryption now becomes decryption. So if you look at the picture, the only thing that happens is for encryption and decryption, where you now basically do a duplexing call with flag is true. And note that the attacker can choose the ciphertext. So the attacker can actually influence whenever you have a flag is true. This also influences the bounds. So these are the algorithms. I will not go into details, But what you see is that in the encryption, you have encryptions with flag is false. It's indicated in red in the left algorithm. For decryption, you do duplexing called with flag is true. You do the same story. Authenticated encryption security model is a bit more complex. I refer you to the paper. So you get a bit more involved triangle inequality. The important thing is that in decryption calls, the flags are false. So if you now do this reduction from a distinguisher, the authenticated encryption distinguisher D, to the duplex distinguisher D prime, this influences the parameters of D prime. So what we see is N remains N, Q is QE plus QD, etc., etc. The most important change is that the number of queries with an overwriting outer part could be huge. Every decryption call is potentially with an overwriting outer part. This results in actually the second term here, sigma D times N over 2 to the C, plus sigma D choose 2 over 2 to the C. And this is an interesting bound, actually. At some point, there was a result of Gilbert et al. At Eurocrypt 23 even, where attack Zodiac. But the only thing they do is basically find a matching attack against this term. Well, it's not even matching, actually, because they take sigma D and N is 2 to the 3C over 4. So if you plug in those values, it's not matching, but they do a different counting. But roughly, this is the matching attack for that bound. To conclude, I want to mention that this generalized key duplex is a very powerful construction. You can do a lot. It's hard to understand what the power of this construction is because it's a very complex scheme, a very complex bound, a very complex parameterization. But if you go to the specific use cases, many of those things simplify. And with these 5 use cases that are in the paper, from truncated permutation all the way to authenticated encryption, we look at these ones from easy to hard. And you can think of many use cases. There is also an interesting one, which is the ISAP authenticated encryption scheme. ISAP was a leakage resilient scheme, and the security of this ISAP scheme didn't follow from the monkey duplex or monkey sponge trap, but it had 2 duplexes in a different way, and it used socks. So by magically combining those results and using this key duplex result as a black box result, you can get good security. I still want to mention, of course, this only holds if this permutation is random. I already mentioned I have a friend who makes a random permutation. I use my random permutation to make my duplex calls, which you can use then. But this all holds under the assumption that this friend of mine made a very good permutation. In the paper, there is much, much more. So this paper, well, it was an e-print already in 22. It's a 23 paper. But there is a lot more history about the duplex, what led to this evolution, how to bound these multi-collisions, much more on these applications, and also the mapping to multi-user security. But overall, I hope I managed to give you a good introduction of well, not sponges. If you want to look at sponges, look at my FSE talk, which gives a better overview in general. For this one, I wanted to give you a more technical overview into what really happens for the duplex and how you can use it hard, what this bound means, that sort of things. And I hope to have given you a good intuition behind this. So thank you.
Thank you, Bart, for the very interesting talk. Do we have any questions?
Yes, I can ask something. So I understand the Gilbert attack and also like this matching attack at the end. It comes from when you do the decryption and you have the different flag, then you can force the input at the permutation, right?
Basically, yes.
Yeah,
So,
yeah,
but there is much more going on, of course. Yes, it's not
yeah,
a
yeah,
simple
yeah.
one. Yes.
I mean, that's the starting point. So I'm sure like like these schemes like Beetle and so on. Would it make sense to generalize the feedback function to include also schemes like Beetles and how that
Yes,
affect?
that's a very good point. I don't talk about this in the presentation. I mentioned this in the note, and that's the cool thing of Beetle, actually. I must admit I like Beetle quite a lot actually. I don't know if one of the designers of Beetle is here, but that's the core part. The core idea of Beetle is basically that you don't do this trick, right? So here the attacker in encryption adds the plain text, but the state, if you look at P after absorbing P1, the outer part is
It's a
not just
different function.
depending on P1. And for decryption, here the outer part that goes to the next duplex is fully in control of the attacker. And the cool thing of Beetle is that this is not the case. At some point, there is a result from some people, I forgot the names, I think ASIACRYPT et al. Would generalize this duplex. We look at the generalized Beetle one. It makes sense to generalize this even further, but that's already somewhat generalized. But that's a very valid point. So the Beetle construction is not covered. I think it's TOSC21, but it could be someone else. I forgot who wrote this. They already look at authenticated encryption based on this duplex idea. It is generalizable indeed to much more. That would be a mix between my duplex guide paper and this one from 21, I think.
Thanks.
Yeah, so just to clarify, it's paper I wrote with Bishwajit and Mridul.
Ah, yes, it was you. Yes,
and the construction is called transform then formute, which is like a generalization of duplex Beetle. We had the construction POC.
Yes, but
so
it's specifically for authenticated encryption.
Yes.
Yes, yes, and the duplex is more general. A bit more general.
Yes.
Of course, even about the main goal of duplex is authenticated encryption, but if you look at these use cases, you can do more with it. But the ones where the flag is true is almost always authenticated encryption. But I can imagine you also use this for PRNGs where you wipe the state to get forward security. That follows in this duplex setting as well. So I'm not
but
sure.
I guess in those settings you don't really. I mean, the decryption issue doesn't really matter in those cases, right?
No, but this would be a duplexing call with a flag is true.
Yes.
But that said, your result from, I think it's 21, right? Could be 23. I'm messing up.
21.
But that's a very good angle to well, it's a good generalization of the duplex actually, of the Beetle actually.
So on this last point, like, has it also been looked at, like what happens when you, let's say, reverse the decryption and encryption? So you use this, like the flag which wipes the state in the encryption, and then the decryption is the other way around.
But you mean you use flag is true for encryption?
Yes.
Yeah, that is not analyzed. I don't think there is a real construction that does this. It reminds me a bit of the Grindal hash function a long time ago, because Grindal was just a sponge, but then with overwriting the outer part. But you just give the attacker more power. So it's typically discouraged to do in general.
Thanks.
And then there is a question from Yaobin. Can duplex results apply to KMAC?
KMAC, that's the standard MAC function based on SHA-3, which is based on the normal sponge. That's actually, if I recall correctly, that is just an authenticated sponge, which is a special case. All these results, these duplex results, apply in the setting as long as the key is at most one block. Which is, as far as I remember, I would have to double check for KMAC the case. But as soon as you would have like an outer key sponge where the key is absorbed in multiple blocks, then the duplexing bound does not apply anymore. But as far as I know, it applies to KMAC, assuming that the SHA-3 permutation is a random permutation.
Okay, thanks. Other questions? Then I guess no. So I think we can end the session here. Thanks again for the
Okay.
very nice talk.
Yes, thanks for listening, everyone, or for attending at least. And thanks for inviting me.